Hi! To be able to analyze the performance of a powertrain, we will in this lecture combine the mathematical models for the different components in the transmission in order to build a complete transmission model. This is a symbolic picture of the key components in the powertrain and how they connect to each other. It shows the wheel connected with gears, which via a clutch is connected to the combustion engine. For completeness, we show that the combustion engine is connected to a fuel tank, even if that is not a part of the transmission model. Notice that we have only modeled one wheel, but it represents all the driven wheels. So the force and torque acting on it in this model is the sum of the forces and torques on all driven wheels. We also combine the final gear and the gearbox into one part, as they can easily be represented by one combined gear ratio. The combustion engine produces a shaft torque of a size controlled by a torque request signal from the accelerator pedal or from the control system. The engine output torque is called TICE and the shaft speed omega IC. To be able to produce the torque, the engine requires a fuel flow from the tank. The fuel flow can, for example, be expressed in kilowatt and is then called P fuel, or it can be expressed as a mass flow rate in grams per second. Our model of the engine is quasi-static, which means that it does not include effects of transients. The quasi-static model is best summarized as an operating range in a torque speed diagram, limited by minimum speed, maximum speed, and a maximum torque limit. As long as the torque requested by the control system is within these limits, it will be possible for the engine to deliver it. For each torque speed point within the operating range, there is also a value of the specific fuel consumption in that operating point. These values are shown as specific fuel consumption contours in the diagram. The specific fuel consumption given by the map will determine the fuel flow from the tank. The clutch is another controllable part of the powertrain. The driver can control the clutch to be closed, open, or slipping. When the clutch is closed, we can model its behavior easily, since a closed clutch is like a rigid drive shaft. The speed on both sides are equal, omega gearbox equals omega ICE. The torque is also the same on both sides. T gearbox equals TICE. In the closed mode, the engine is connected to the rest of the transmission and can propel the vehicle. Since both the speeds and the torques are the same on both sides of the clutch, the power will be the same on both sides, resulting in no losses in the clutch when it is in closed mode. The clutch can also be open. In this mode, the engine is not influenced at all by the rest of the drivetrain. The speed of the gearbox is completely independent of the engine speed. It can be both higher, equal to, or lower than the engine speed. Since the shafts on both sides the clutch are not connected to anything, they both have zero torque. As the torques on both sides the clutch are zero, the powers on both sides are also zero. This means that there are no losses in the clutch, also when it is in open mode. When transitioning between the two other modes, the clutch can be controlled to slip. In this state, the speeds on both sides are different, but the clutch can still transfer a torque, so T gearbox equals TICE. If the torque on both sides is the same, while the speed is different, the power on the side with higher speed will be higher than on the side with lower speed. As a result, the clutch will always have losses when it is slipping. The losses become higher the speed difference and the higher torque the clutch transfers. These losses will both cost extra fuel, and if they remain for any longer time, they will overheat the clutch. Therefore, the clutch should only be in the slipping mode for a short time when transitioning between closed and open mode. The transition typically takes in the order of a second or less, except for in a few extreme situations, like starting in a steep uphill gradient. The next step in the transmission model is the gears. This part of the model includes both the gearbox and the final gear. The gearbox has a number of different gears which can be selected by the driver or a control system. The output speed omega wheel equals the input speed omega gearbox divided by the total gear ratio I gear tot. As the gearbox has several selectable gears, the gear ratio has different values for different gear number k. The torque out T wheel equals the torque in T gearbox times the total gear ratio. The final part in our transmission model is the wheel, which converts a rotating movement to a linear movement. The model of the wheel is similar to a gear model, only that gear ratio is replaced by 1 divided by the wheel radius. This is the model of the wheel. The vehicle speed equals the angular speed of the wheel times the wheel radius, and the traction force on the vehicle equals the wheel torque divided by the wheel radius. Notice that the wheel speed has to be expressed in radians per second and the wheel radius in meters to give the vehicle speed in meters per second. Now we have gone through the model of the parts in the transmissions and have reached the traction force and vehicle speed. This is the force and speed we have analyzed earlier with the vehicle model. So the force and speed from the wheel model will be the same as the vehicle operating point in the force speed diagram. If the engine is propelling the vehicle, the clutch is closed, except for short times. When the clutch is closed, we can combine the models of all the components in the transmission into one transmission model, which describes the relation between engine shaft speed and vehicle speed, and another relation between engine torque and traction force. The vehicle speed equals the engine angular speed multiplied by the wheel radius divided with the total gear ratio. The traction force equals the engine torque multiplied by the total gear ratio divided by the wheel radius. Notice that even though the transmission consists of many parts, its overall function is very simple. The transmission model can be used to calculate the vehicle operating point from the engine operating point, or vice versa, to calculate the engine operating point from the vehicle operating point. Shifting gear will change the total gear ratio and thus change what engine operating point corresponds to a specific vehicle operating point. We have so far only discussed the losses of a slipping clutch and neglected all other losses in the transmission components. The losses of the clutch are important to understand as they significantly influence how the clutch can be used. The other losses are, however, often possible to neglect as the function of the transmission and how it is controlled can be understood without including losses. In many types of investigations, the results are also quite accurate, even if the transmission losses are neglected. For example, when selecting gear ratios, sizing engines, or determining which gear is the most efficient to use. One example when transmission losses are often important is when analyzing fuel consumption or electricity consumption. When simulating, it is easy to include even fairly detailed loss models as they are just some extra code inside each component model and they do not influence how the overall simulation model is built. In this course, we will often allow ourselves to neglect transmission losses, but several types of losses are modeled in the QSS simulation models. Now we have derived the transmission model from the component models, and the main result from this lecture can be summarized. The transmission can be analyzed using one combined model. This model can translate engine shaft speed to vehicle speed, or vice versa. And it can translate engine torque into traction force, or vice versa. This means that when the engine is propelling the vehicle, each operating point in force and vehicle speed corresponds to an engine operating point in engine torque and shaft speed. Now we hope that you have a good understanding of how to analyze the transmission. You can test that in the following exercises. If you have any problems with the exercises, please post them on the discussion forum.